could be applied in particular to dark matter direct detection. So Achim, when you want, please. Thank you very much.
Okay, great. Thanks a lot, JJ. You maybe have to also turn off your... Okay. Thanks a lot, JJ, for giving me the opportunity to discuss our work and for inviting us to San Sebastian. I understand the audience is very diverse, and so I would like to start with a general introduction and then show you what we have done in terms of using this theory called chiral effective field theory for understanding the nuclear physics, the strong interaction physics involved in dark matter direct detection. Also, if you have any questions, I would very much prefer to have questions in between, so just stop me. We can discuss in between, and I'm happy to skip any parts of the talk. Okay, so as you know, there are four fundamental interactions in nature: gravity, the weak interaction, electrodynamics, and the strong interaction. And of course, there are certainly some parts of these interactions that are better understood. For example, I think it's fair to say that we have a fairly good understanding about how the periodic table of elements, how the structure of atomic atoms, the atomic structure emerges from electrodynamics. In this talk, I will focus on one of these four fundamental interactions, namely the strong interaction, which we know is governed by quantum chromodynamics, the interaction of quarks and gluons. And this is this theory is responsible for binding quarks together in hadrons, so here in this picture in neutrons and protons, and also for binding the neutrons and protons in atomic nuclei, in the nucleus in an atom. Okay, actually this interaction is entirely responsible for the ordinary matter in the universe, for the energy budget that goes into ordinary matter. This is all QCD physics. And so in this talk, while I will focus on the strong interaction physics side here, at the beginning, we want to use later what we know about nuclear physics and strong interactions, how it plays out for dark matter direct detection. I also wanted to show you where we are in terms of understanding nuclei from the ground up. So basically from the step of neutrons and protons that are bound here in the alpha particle, helium-4, where we are in terms of understanding the rest of nuclei. So what is shown here are all nuclei bound by the strong interactions. So they're in what we call the nuclear landscape or the nuclear chart. Every nucleus is a dot here for a given proton number Z and a neutron number N. So helium-4 would be down here. And it reaches all the way up to very heavy nuclei. And today we know about 3,000 nuclei that have been discovered of in total 118 elements. About 10% of the nuclei discovered are stable, so roughly 300 stable nuclei. And as you know, if we add neutrons to stable nuclei, nuclei become unstable, they beta decay, but there are many bound by the strong interaction. And between these two lines here, the so-called proton trip line, up to where protons still stick to the nucleus, afterwards they trip out, so no particle-bound nuclei exist. And over here, the neutron trip line, where you can add many neutrons and the nucleus still is particle-bound, but just decays by beta decay. So between these two limits of the nuclear landscape, all of these nuclei exist. And there was this pioneering paper cited here, which predicted that there are as many nuclei unknown, roughly 4,000 plus or minus 500 isotopes, that in particular are extremely neutron rich over here. Okay, so in terms of a strong interaction, all of this follows from QCD, where the proton trip lines are, where the neutron trip lines, what the structure is of the nuclei in between. And that's the prime driver for three large facilities. There are many smaller facilities, but three large facilities. One already driving away, which is the RIBF facility at Weeken, which is really fantastic in this lower part of the nuclear chart. Another facility for rare isotopes, or in particular neutron-rich isotopes at MSU, which is just starting to go operational, which will focus on the second half here of the nuclear chart, and a facility under construction in Darmstadt, FAIR, Facility for Antiproton Ion Research, which is focusing more on the neutron-rich side up here. Okay, and all of this basically is strong interaction physics. I want to focus in this talk about the strong interaction physics for dark matter direct detection, and I want to give you a bit of an outline of what I would like to discuss. First, I want to highlight here that this is basically a series of work done with two former postdocs, Martin Hoferichter and Javier Menendez in Darmstadt, who are now Martin's in Bern and Javier is in Barcelona, and a former graduate student, Philip Close, who's now left academia, but did a lot of pioneering stuff here together with Martin, Javier, and me. So I first would like to talk a little bit more about this theory from the title of the talk, chiral effective field theory, and tell you what it does for understanding the interactions of neutrons and protons in nuclei and what it predicts for nuclei. Because whenever you have a theory, it's helpful to do a sanity check and make sure that it predicts things that have been measured before we go to dark matter direct detection. And then I wanted to go through essentially here in a more chronological way of how we started to work on this, to first discuss WIMP nuclear scattering when the WIMP, the dark matter particle, couples to the spin of the neutron and proton. So this is called spin-dependent WIMP nuclear scattering, and there's many interesting QCD effects that are important to encode in the response of a nucleus to scattering of a WIMP. Then I would like to discuss what happens in case of an inelastic scattering when WIMPs scatter off of the nuclear ground state and may excite the nucleus in the scattering process. This is very, very hard to detect and maybe even impossible to detect, but it has a lot of neat features. And since JJ is always looking for challenges and new ideas, I thought this would be the perfect place to also mention this. And then I want to talk a little bit more about spin-independent nuclear scattering. So where basically all of the neutrons and protons in the nucleus pull the same way, and you get a very much enhanced response for a large nucleus, which is one of the motivations for doing dark matter direct detections with large nuclei. I want to show you some results where WIMPs not only interact with neutrons and protons, but with other hadrons, with pions, and we did a first limit on WIMP-pion interactions together with a xenon 1-ton collaboration. And then I want to point you to that there's basically all of these response functions in form of Jupyter notebooks that you can use on our website, and basically the same type of response functions also are important for coherent, so for elastic neutrino-nucleus scattering. Okay. So let's start with the first one here to discuss more about chiral effective field theory is. So when we want to describe a nucleus, so here's a cartoon of a nucleus, any of these nuclei here on the nuclear chart, we really want to describe this from the bottom up based on this theory of strong interactions. And there are two ways to do this. One is a straightforward way based on the QCD Lagrangian, and to simulate really for like the deuteron, so 2-nucleon system, a 6-quark to 6-quark correlator, and calculate this using QCD on a space-time lattice, or lattice QCD. This is possible for few nucleon systems, let's say up to the alpha particle, but with large challenges in terms of signal-to-noise ratios and with very few calculations at or close to the physical pion mass. For everything else heavier than an alpha particle, you will now and in the future need effective field theories of the strong interaction, which are based on the relevant degrees of freedom for nuclei, namely neutrons and protons. So we will work with effective field theories of QCD. And the prime effective field theory for QCD, which we will use is a theory that was put forward by Steven Weinberg a little over 30 years ago, called chiral effective field theory. It's called chiral effective field theory because it includes neutrons, protons, and the Goldstone bosons of chiral symmetry breaking of QCD, which are the pions. So Weinberg basically told us that instead of organizing the theory in some kind of perturbative small coupling expansion, we use an expansion where we don't expand in a coupling, but we expand in the momenta. So we look just at QCD at low energies or low momentum scales, which is what this picture is about, right? It's nuclear dynamics at low energies. So we can expand not in couplings, but in small momenta over a scale where this theory breaks down. And Weinberg, in fact, predicted that at leading order, so in case you're interested in really low momenta and energies, at leading order, they are just interactions between pairs. So neutrons interact with neutrons, protons, and two protons. So these lines are neutrons and protons, and they have a contact interaction or a short-ranged interaction, and they can exchange one of these pions, one of these Goldstone bosons. And because we include the pions here at leading order and at all other orders, this theory is called chiral effective field theory, and basically is based on the symmetries of the strong interactions on this chiral symmetry and its breaking of QCD. Okay, so you can view of this as like a double expansion. You expand the long range part of the interactions in pion exchanges. So at the longest range is one pion exchange, and then you get to closer distances between the nucleons, and there are two pion exchanges, and you expand the short range part of the interaction between nucleons in terms of contact interactions. So it's some like smeared out delta functions and derivatives of delta functions. Okay, and basically the power of the theory is that it organizes everything systematically in orders of Q over this breakdown scale. Okay, then a few years later, Weinberg's student Van Kolk was the first to show that there are also three body forces here. However, they come in, so this was 94, however, they come in at higher orders. So if you go to not leading order and next to leading order, but you go to next to leading order in this theory, the theory predicts three body interactions, and for nuclei, they play a very important role, as I will show you later. Okay, and then at the next order, there are subleading three-body interactions. There are also four-body interactions that are predicted. Now, whenever you hear many body interactions, sounds like many new parameters. But in fact, because of the consistency of these interactions, and in particular this long-range chiral physics, these couplings, for example, which are circled in blue here, that determine the most important part of the three-body force, also have already entered the two-body interactions, and so there are no new parameters. So in fact, for many body interactions, there are very few short-range couplings that you need to adjust. In practice, there are just two. And so we can make a lot of predictions, and we can understand how precise or how accurate is the theory by calculating to a particular order and then going to the next order and seeing how things change. So this is a systematic expansion. The expansion parameter is this momentum scale Q, which is maybe say 100 or so MeV over a breakdown scale of 500. So the expansion parameter is roughly a third. We can obtain error estimates. And what's really important for this talk, we know how to couple in electroweak interactions. We in principle know how to match to lattice QCD. If we would have a real BSM theory that would be valid at the quark and gluon level, we could do that. And so we know how to couple in WIMPs or any other particles, and going basically from quarks and gluons to nucleons and pions. Okay, so I want to describe how this theory is important for dark matter direct detection. Before going to the dark matter direct detection or WIMPs coupling to neutrons and protons, let me, there's a question in the chat. Maria Pilar, do you want to ask? You can't use the speaker. Do you want to type your question?
Yes.
And we just heard you too, so maybe you can.
Okay, you can hear me?
Yeah. Yeah, we can hear you.
Okay, no, my question, you said that there are very few parameters, but I mean, standard IPT for.
Now we can't hear you. Okay, maybe you type your question, Maria Pilar.
So can you hear me? Sorry, I don't know, I don't have the mute button or anything like that, so. My question was, you said that there are very few parameters, even if you go to higher orders. This is not a standard thing in some IPT, for example. So.
Okay, I think I understand. I think I understand your question. Let me repeat it to make sure that I got it. So you're asking about going to higher orders, where there are more low energy couplings. Is that correct?
Yes, normally when you go to higher orders, there are many more couplings.
This is also true here. This is also true here. So at leading order for the NN interactions, there are two couplings. At NLO, there are of the order of 5 or so. Then at N2LO, there are no new low energy constants in the NN sector. All of it is basically from pion, nucleon, chiral perturbation theory Lagrangians. And at N3LO, there's of the order of 15 or so new couplings. So it's true that in terms of contact interactions, there are many contact interactions that need to be determined and fit to experiment. What I meant in terms of there being less couplings is related to the many body interactions, and they start only at higher order themselves, and they have a lot of couplings that are consistent, that are shared between the 2 and 3 body world. And for that reason, if you wanted to go, say, for example, a complete N3LO calculation, which we have done only for neutron matter at this stage, complete N3LO calculations, then, or nuclear matter, then there are just these two couplings here. Everything else is chiral perturbation theory Lagrangians, which have been well determined in the pion-nucleon sector already. So what I meant was maybe to specify the answer. If you go to a nuclear system, the many body interactions have only very few new low energy couplings, and that's because of the fact that the NN sector has been determined and the pion-nucleon sector has been determined. So there are not many new couplings that need to be fitted to nuclei. Thank you for the question. Okay, so then before we move to dark matter direct detection, let me show you just a few slides about how this theory is actually working. So there has been dramatic progress in nuclear physics in calculating nuclei, really, by starting from these chiral interactions, so taking some 2-body interactions and 3-body interactions up to some orders, and calculating nuclei from the ground up, meaning basically with only controlled many-body uncertainties. And at this point, actually, in the field, the many-body uncertainty is much smaller than the Chiral EFT truncation uncertainty from what's left off, or off, say, if you do an N2LO calculation, you leave off the N3LO physics. And we can calculate nuclei much better than the Chiral EFT expansion or the EFT truncation uncertainties. And here's a collection from a colleague at MSU, Heiko Hergert, who has basically colored every square for nuclei that have been calculated in what we call ab initio calculations, this based on Chiral EFT. So you can see that really lots of the lower part of the nuclear chart is colored in. And here just an example for the oxygen isotope. So this is down here from the most neutron deficient or proton rich oxygen isotope all the way up to the neutron drip line here at oxygen 28 and even beyond. You can see basically a whole bunch of symbols. These are all different many-body methods that start from 2 and 3 body interactions and agree within, let's say, a few percent uncertainty. If you would add on top of here the Chiral EFT truncation uncertainty, this would be a much larger error bar. Okay, so basically we can solve like up to, as I will show you later, even up to a 100-body system, basically with controlled many-body calculation uncertainties. Here's another example from a paper that, or here's an example of, we were also involved in some calculations here, but from a recent paper we did where we calculate the lightest 700 nuclei in the nuclear chart. And here we were more interested in this figure to see where is the probability based on these uncertainties large that nuclei are particle bound. So particle bound nuclei means blue. And you can see here that that agrees very well with these drops, which is the proton drip line that has been confirmed experimentally. So these chiral interactions do predict not just with the overall features, but also quantitatively the nuclear landscape. And the same is true over here where the neutron drip line is known. As an example, let me also take a random chain here, for example, in the middle, which is the chlorine chain. Proton number is 17, and here you can see single neutron separation energies, 2 neutron separation energies, and the same for the protons. The black bars are experiment, and the red points and regions is the theoretical calculation. There's nothing adjusted to this particular chlorine chain. It's just taking 2-body interactions and 3-body interactions that have been fit in the 2 and 3 body sector based on this Chiral EFT. So basically there's lots of, as you can see from the previous slide, basically lots of new calculations for nuclei based on chiral effective field theory. So the field of nuclear physics has really changed in this perspective, and very few models are used to describe nuclei, say up to 10. I would have some time, if I had more time in the talk, I would also like to show you that the same Chiral EFT provides very important constraints for neutron stars, which is basically a gigantic nucleus with a baryon number not being 10 to the 2, like 100, but being baryon number 10 to the 57, but also aspects of this neutron star can be described by chiral effective field theory. So this Chiral EFT really bridges the lightest nuclei up to neutron stars, and I want to next show you a little bit about what it does for dark matter interactions. What's important for dark matter interactions, say if you would have a WIMP, chi or X here that scatters off of a nucleon, a single nucleon, then there's some mediator, some current interactions between WIMPs and a single nucleon. And because we're doing this in chiral effective field theory as a systematic low energy theory of QCD, there's a similar chart. It just hasn't been as much explored, but a similar chart. And that says that at leading order, the interaction is just of a WIMP with a single nucleon. Okay, so we call this a one-body current because a WIMP couples to a single one-body nucleon. Okay, and for this particular graph is here for axial vector currents. So this would be for spin-dependent interactions, or if we do without WIMPs, if these were leptons, this would be beta decays. There's a one-body current at leading order, and also at the next to leading order Q squared, there's also a one-body current. So this would be basically, if we would do it for beta decay, this would be Fermi's theory of weak interactions, and the Q squared correction would be radius corrections because the nucleon has a finite size. However, if you couple a WIMP to nucleons in a nucleus, or even just to 2 nucleons, then at higher order, just like there were 3-body interactions in addition to 2-body interactions, the WIMP can not only couple to a single nucleon, but it can also couple to 2 nucleons. So there's not only couplings of the WIMP-mediated current to a single particle, but there's also the WIMP-mediated current coupling to 2 nucleons, and we call these two-body currents. They enter just like the three-body force in this particular scenario for axial vector currents at N2LO. And here, in particular, for the axial vector currents, there's even a lot of similarities to these other two and three body interactions circled in blue here, because the pion is also an axial vector nature. And so basically these couplings here are determined from the chiral Lagrangians. Okay, so but for this talk, this is maybe a smaller detail. Just keep in mind that in addition to single nucleon currents, WIMPs can couple also to two nucleons. And again, this has been tested not for WIMPs, but for beta decays. So for example, I took two things here for electroweak interactions. So the left side is for weak interactions, the right side is for electromagnetic interactions. Maybe we start on the right because it's easier. There have been a lot of works on magnetic properties of light nuclei. Much of this has been led by Saori Pastore and collaborators. And here I just take a recent example from this in a magnetic dipole transition for lithium-6. And if you include only one body currents, so the photon couples just to neutrons and protons, then you get these results. But if you want to be consistent with experiments, you need to include two body currents. So there are important effects of two body currents in light nuclei. The sort of order of magnitude is 10%. And in heavier nuclei, the impact is larger. This is here for a weak interaction. So this is the beta decay of tin 100, an incredibly rare nucleus, which has been measured because it has such a large beta decays. And you can see here different calculations. This chart is maybe a little bit busy, but you can see here that there's lots of open symbols. These are the open symbols that correspond to including just one body weak interaction currents. And if you include these chiral currents that are largely predicted, then you get down to these filled symbols, and you can see all the filled symbols are closer to the two most recent experiments, which have still relatively large uncertainties. So these two body currents are very important. And if you're into weak interaction physics or into double beta decay, then basically all these two body currents play a leading role to understand what is known as the quenching of beta decays. Okay, maybe just to show that effective field theories in general are also predictive. Here's not chiral effective field theory, but let's say even lower resolution, lower energy effective field theory, which works particularly well for heavy nuclei. And in this work here with Tonio Coelho Perez and Javier Menendez, we looked at two neutrino double beta decays or two neutrino double electron captures. And you can see that we predicted lots of cases, and in this with EFT uncertainties. These are leading order uncertainties, so they're pretty large. But what is nice here is that in the cases where they have been measured, they agree very well within uncertainties, and these are sort of 68% uncertainties, so there should be some outliers. In this earlier paper, we were completely unaware of xenon, and so we quickly rushed to make also an effective field theory, but also a shell model prediction for a double electron capture on xenon 124. This is the effective field theory prediction here based on a similar math strategy as above. And this is shell model prediction, and we were, of course, we were thrilled that this agrees very nicely with the recent observation, and this is the more recent update from the xenon 110 collaboration. Okay, so I think these effective field theories are working very well. They, of course, have uncertainties, and there's a big effort in the community to understand better the EFT truncation uncertainty and the many-body uncertainty. Okay, so with this, I'd like to move on to the original target here, namely to look at dark matter direct detection, and give you basically the, without much detail, the basic results. Okay, so we assume that the dark matter particle is WIMP, and we're interested in direct detection, so WIMP scattering off of nuclei. And there are basically two inputs that one needs. One is one I will not discuss a lot, but we've worried about a lot, namely how to go from the WIMP quark gluon level to embedding the WIMP coupling to nucleons and pions. And then the part that I will discuss more, which is the response function, namely, or the condensed matter, the structure function, where a WIMP scatters of a many body system, an atomic nucleus like xenon, which has 130 nucleons. And if you look at the kinematics of dark matter detection experiment, the typical momentum transfer from the WIMP to the nucleus is small, or at most of order of the pion mass. So that's the prime area for chiral effective field theory, because the momenta are in fact low, where this EFT is working very well, as I showed you. Okay, and in general, also we have this. This has the goal to really incorporate what we know about the strong interaction physics, so that when there's a signal, or when we do some BSM searches like in sevens, that we can really say what's QCD and what's BSM. Okay, so this is on an energy scale again. I will focus at the low energy scale here, but basically we know how to go from WIMPs coupling to quark and gluons to effective operators. Then there are some electroweak running, and that in the end gives us WIMPs, now X couplings to nucleons, and I will also show couplings to pions. And we have to embed them in calculations for nucleus. So these are like the nuclear ground states, or in the case of inelastic scattering, going from a nuclear ground state to a nuclear excited state. Okay, let's start with spin-dependent WIMP-nucleus scattering. Okay, so actually we got involved in this because of a colloquium of Laura Baudis in Darmstadt in 2012, and were amazed of the kind of level of nuclear physics that was used in analyzing the experiments, and we wanted to contribute to this. And that's why most of the work initially was focused on xenon. For xenon, we use basically what is called a valence shell Hamiltonian. So this is based on two-body interactions with some corrections, because in this heavy region, we are not able to include three-body interactions in an accurate way yet. And then we diagonalize this Hamiltonian in large valence spaces, like with dimension of many body dimensions up to 10 to the 9. And as a first test, we can compare what the spectrum, this is now for the odd mass xenon isotope xenon 129, the calculated spectrum compared to experiment, and xenon 131 calculated spectrum compared to experiment. And you can see that in general, the ordering of states and the grouping here, 2, 4, or here 3, 3, 3, 3 is very well reproduced. So this is for nuclear physics a pretty good agreement for the spectra. Okay, yeah, and as I said, all this region is of course very interesting, because there's beyond WIMP direct detection, there's lots of double beta decay physics and sevens physics going on in these for these target nuclei. Okay, and then we want to calculate the differential cross-section of a WIMP scattering off of a nucleus as a function of momentum transfer. In general, for the response functions, so that's this differential cross-section is decomposed of couplings with some response functions, and all of these couplings are sensitive to different channels. So the top line here is spin independent. That's the usual spin independent, isoscalar, isovector spin independent. And then we can also couple to pions, as we will see later. And this is the spin dependent channel. I will first now discuss spin dependent interactions. And so now we want to calculate these response functions, which is basically sandwiching the WIMP single nucleon or WIMP-2 nucleon currents inside ground state wave functions that come out of these large calculations. I want to point your attention to that there is a lot of interesting work, as we discussed at the beginning, on using ab initio calculations, like what I showed you for the oxygen chain, also for heavier nuclei. And there was actually a very nice paper by Baishan Hu and collaborators that appeared a couple of months ago. However, for heavy nuclei like xenon, the spectra based on different 2- and 3-body interactions here are still a little bit, we still need to understand better the theoretical uncertainties here. That's why I want to use these valence-based Hamiltonians for the time being. Okay, so let's look at the spin 2 isotopes, xenon 129, which has a 1/2 plus ground state, and xenon 131, which has a 3/2 plus ground state. So they have some non-zero spin and therefore contribute to the spin-dependent WIMP-nucleus scattering. Okay, so then we can calculate the spin-dependent structure functions or response functions for xenon 129 and xenon 131. And here we will follow what the experimentalists like to do, namely to characterize this response function, assuming that calling it WIMPs coupling to neutrons. This is the neutron response function, WIMPs coupling to the protons. Okay, because xenon is an even number of proton nucleus. Basically, all the protons are paired, and also almost all except for one of the neutrons are paired, because nuclei have pairing and are finite superfluid systems. And so you can couple dominantly to the neutrons because it has an unpaired neutron. And in fact, the structure factor is of the order of the spin expectation value, or the spin of the neutron. At low momentum transfers, this is exact. Okay, so at 0 momentum transfer, this axis here, this is basically representing the cross section. At 0 momentum transfer, the response of the nucleus is dominated by the neutrons. Okay. However, I also told you that let's assume that the WIMPs couple to the neutrons only. Then there are 2-body corrections where the WIMPs couple maybe to the neutrons, but there are also neutrons and protons here. Okay, so because of the strongly interacting nucleus, the single coupling to neutrons only doesn't really exist, because they are always immediately at this subleading correction, there are also couplings to protons. And once this is included, the response gets much more interesting. And so here you can see the response to a single neutron interaction, assuming neutron only coupling gets shifted because of this, it gets a little bit weaker. But this is a kind of a small effect. However, for the species which originally is all paired, coupling to the protons, when the 2-body currents are included, the response is increased by almost an order of magnitude at low momentum transfer. Okay, so that's basically saying that if you assume WIMPs coupled to proton only, then it can still connect to the neutrons, which have large spin expectation values. So the response for the cross-section at low momentum transfer will follow the shape of the neutrons. It won't be quite as large, because this is a subsat-leaving effect, but it will be an order of magnitude larger than assuming the protons inside the nucleus don't interact at all. Okay, so these 2-body currents enhance the coupling to all the even species where you would never expect a large spin response. Okay, I just want to say that we actually improved the calculation a little bit. So there's also a newer calculation where we reduce the uncertainty bands by doing a better calculation. But you can see that the uncertainties old, which were large, and new, which are new, are consistent. So that's also nice about these EFT uncertainties. And then let me show you all the other responses besides xenon, which we calculated later then. And you can see in all of these cases, let's say germanium, this effect that the WIMPs coupling to neutrons get a little bit modified, but the WIMPs coupling to the originally basically suppressed species get enhanced a lot and follows that of the neutrons. You can see that in all other spin-dependent isotopes. Okay, so let me show you what that does. Here's first the limits on limits on spin-dependent WIMP-neutron interaction. So we were very fortunate that immediately after we finished the calculation, 2012, for xenon isotopes, the xenon 100 collaboration then picked it up. And in fact, for all the spin-dependent xenon limits, our calculations have been used as the response, as the differential cross-sections. Okay, and so this is xenon 100, and I just picked the old one for a reason that I want to show you now, and this was, for example, Lux recently. And it's important to compare these limits, also to use exactly the same nuclear physics response functions. Okay, now if you looked very carefully at the xenon 100 paper, and you looked at the WIMP-proton limits, so let's look at this a little bit more in detail. For the WIMP-neutron, spin-dependent WIMP-neutron limits, going from xenon 10 to xenon 100 was like an order and a little bit more improvement in sensitivity. If you look at the WIMP-proton limits, spin-dependent WIMP-proton limits, going from xenon 10 to xenon 100, there were 2 orders of magnitude improvement. And the reason that the experiment suddenly got more sensitive to the WIMP-proton coupling, because they included the response functions, which included the 2-body currents. So this enhancement here is important for limits, and it makes a detector more sensitive to the even species as well. Okay, so I think this is still important. JJ, you have your hand up.
Sorry, it's me again. I'm not. I somehow connected through the link that doesn't show my name. So it's Pilar again. So
Hi, Pilar.
let me understand you. So you're saying that, I mean, the xenon 10 limit did not include this this effect that you were showing,
Yes.
of the 2-body interaction. So in fact, what one should get from this is that that limit is wrong, no? I mean, it would be better if they would.
Exactly.
It would be better. Okay, so so one should really redo the.
This was with
the limit. Of course, it's very complicated because it's an experimental limit, and I mean, just doing a recast with a new things might not be easy, but in principle, one should not compare these 2 limits, right? That's what you're saying. Okay.
No, I didn't want to. This is already the better limit at the time, xenon 100. I just wanted to use this to show you that actually this chiral physics, and in particular these body currents, have an important role and improve the sensitivity for xenon detector to the spin-dependent WIMP-proton couplings. And these, since then, xenon 100, xenon 110, Panda X, and Lux all use the same response functions with the 2-body currents included.
Okay, thanks.
Thank you for the question again. Okay, now a couple of words on WIMP inelastic scattering and JJ. I have about 5 or a bit more minutes left, right?
Sure.
Yeah? Or you said 45 minutes is a good time, right? Okay, so let me talk about this detection channel because it's very interesting. Okay, so here's the spectrum again for the odd mass xenon isotopes, and you already saw that they have this structure here. For xenon 129, the excitation energy is 40 kilo electron volt, and for xenon 131, it's 80 kilo electron volt. And so, in fact, if you increase the momentum transfer in this elastic scattering experiment, at some point you will open up to an inelastic excitation. So you take the nuclear ground state and you excite it. Okay, and so we calculate also not just what we showed before, which were the elastic, so ground state to ground state transitions with 2-body currents, where the structure functions or response functions have this general fall-off form. We calculated also the inelastic contributions, where you go from the ground state initially to the excited state. Okay, and since xenon 129 has a much lower excitation, factor 2 lower excitation energy, the inelastic excitation is more important there. And in fact, around 150 MeV momentum transfer, which is around here, it even is more important for a scattering experiment than the elastic channel. For xenon 131, it becomes close, but it doesn't dominate. But at some point, they're all as important, the inelastic channel, as the elastic channel.
Sorry again,
Okay,
I'm a bit confused here. So, I mean, given the difference between the experimental and the theoretical prediction for the splittings that you are showing on the right, I mean, so it would look like actually the experimental would tell you that the splitting is much bigger, so no, so than, you know, for 429 than 431, is that?
So what
I
we
mean,
do
even
is
though
we
even
take
the
a calculated
theoretical
structure of these states from theory, and to really make a calculation of the response functions, we take we take the, I mean, 40 and 100 kV are all at the nuclear scale very small numbers, right, for strong interaction physics. The total energy of xenon is about 6-7 MeV per particle, mega electron volt, and now we're calculating small splitting. So we're already very happy about this overall behavior. So what we do is we take the structure of this nuclear state as initial state, calculate it, and the structure of this nuclear state as the final state for the inelastic excitation. And then we take, in terms of the kinematics, the experimental splitting, the 40 keV.
Okay.
This is often done to adjust the threshold to agree with experiment. I mean, what's important is sort of this spin 1/2 or 3/2 tells us how the spin flipped in the nucleus, which is of course important for spin-dependent inelastic scattering, because there you do a spin coupling and you can have these excitations. Okay, so what you can see here is that for the odd mass cases, the inelastic dominates or is comparable to elastic at momentum transfers, which are large and on the upper side of the experimental sensitivity window. So then we folded this into a recoil spectrum, which is what is looked at experimentally. And then this picture here is assuming the WIMP mass is 100 GeV. And then how the recoil spectrum changes, if you look at the total elastic spectrum here, which is the purple hatched one here. So it just is this experimental fall off, which follows basically structure factors. However, if you look at the inelastic channels, then once one of these inelastic channels opens up, you get an increase of the recoil spectrum. So this is the xenon 129 opening up. And then you get another bump for when the xenon 131 opens up. So if you were able to see something like this, it's very interesting, because from the relative size of these bumps, you can learn something about what's the dominant interaction channel, whether this is actually spin-dependent WIMP inelastic scattering or spin-dependent WIMP inelastic scattering. And then also, if the WIMP mass is too low, then even though the momentum transfer is 100, maybe 100 MeV or so, then because of the smaller reduced mass, then you cannot open these two inelastic channels at all. So for example, if you would just see one bump, this would tell you that the WIMP mass would be low on the lower end, for example. So from these relative sizes, these bumps, you would be able to tell you about the dominant interaction channel and about the mass of the WIMP in the same experiment. So it would be a great thing to see. Just in terms of experimental reality, notice, of course, that it's even an order of magnitude more challenging to get to than the spin-dependent limits, and already spin-dependent limits are smaller than the elastic ones. Okay, but I mean, fascinating from the perspective of using the nucleus as a laboratory. Then maybe just two more slides, one on this and one on this one here. So this is maybe a little bit busy, this slide, but in terms of spin-independent interactions, the differential cross-section for, again, WIMP scattering off of a nucleus, spin-independent, can have a number of terms. There's first this usual way, that's A squared enhanced, the isoscalar WIMP-nucleon coupling basically, although there are some radius corrections. Then, as I will show you on one of the next slides, the WIMP can couple also to the pion. These are these two response functions. And then there's a series of papers that suggest Q squared momentum suppressed responses and even more momentum suppressed responses. Okay. And we basically, I mean, that to convince you that we did this, we have a gigantic table in our paper and we look at every nucleus WIMP-nucleon or WIMP-nucleon and then going to WIMP-nucleon and pion coupling that remains coherent. So it scales with a number of nucleons. And that's basically this channel here, which is the usual channel. WIMPs coupling to pions are also coherent. And there's some particular response, which is called this phi double prime response, which is also coherent. The physics picture is here that in a large nucleus, you can have a lot of nucleons occupying the same shell, and this fraction of nucleons then remains coherent, however, with this momentum suppression. Okay. Now, all of these ones here are basically some QCD effects. You get them from just embedding quarks and gluons inside a nucleus. And these are like generic, let's say, beyond QCD operators. And I just wanted to show you with this overview of different response functions. It's very crowded and maybe too technical, but the main take-home message is that there's a whole bunch of responses that are large. So now this is much larger than for spin dependent because the nucleons scale coherently. So the response function, the largest one goes like A squared, so 132 squared. There's a whole bunch of large ones. And if you look into where the large ones coming, then they are all dominant QCD effects. Okay, so all of these are due to the first line on this complicated response function. Okay, so lots of QCD effects. And then there have been many people worrying about non-QCD operators or new operators in dark matter direct detection. They are in fact 4 orders of magnitude even smaller. Okay, so it's really important to get the QCD effects for the nuclear physics strong interaction effects right for these response functions. Okay, and one of these nuclear physics effects, which is particularly coherent, is this WIMP-pion interactions. This is maybe the last thing I want to show you here. So in this case, the WIMP scatters off not just the neutron or protons, but it connects to the pions that are exchanged. Okay, so the pions also consist of quarks and gluons. And for particular couplings, you can couple WIMPs more dominantly to the pions. Okay. Now this two-body current is basically the way how this coupling goes. You couple it to the pions. And if you look at this contribution is suppressed from the chiral counting, but because pions are also many of them holding the nucleus together, so there's also some coherent enhancement. And in fact, we found that if you compare this WIMP-pion interactions, they are after the standard spin-independent channel, so where at low Q, the response is basically fully coherent, goes as A squared. Then the next coherent A squared response is this pion WIMP-pion channel. And basically there are some kinematic 1 to 2 orders of magnitude down, and it's still much more coherent than the spin-dependent interactions, which are order 1 responses. Okay, and in fact, with xenon, we implemented our response function for WIMP couplings to pion to provide first limit on WIMP-pion couplings in this paper a couple of years ago here, which is shown here. There are no other limits on this plot because none of the other experiments have looked for WIMP-pion couplings. This was the first one to do this. Okay, so with this, let me take you to the end of my talk. And I wanted to say that there are 2 nice resources which we're happy for you to use. We have this Chiral EFT for dark matter Jupyter notebook, which anybody can use to calculate the response functions that I discussed in this talk. You go on this website and you can get some instructions. And if you have any questions, you can also email me or ask here. And also I wanted to point your attention to that we did a similar EFT analysis and nuclear responses needed for coherent elastic neutrino-nucleus scattering. So if you're interested in those experiments, I know some of you are, you can also use our response functions, which are based on the same calculations and also include 1 and 2 body current effects. And so with this, let me take you to my summary. So first of all, let me acknowledge again the work done together here with Martin, Javier, and Philip, which I discussed. I hope I could give you a pedagogical introduction to chiral effective field theory and how it's used to describe the interactions of neutrons and protons, nuclear forces, 3-body interactions, how it's used to describe coupling of external probes to nucleons and nuclei, and that it's particularly important, just powerful for low energy nuclear physics, so the nuclear chart, but also for WIMP dark matter direct detection. And I hope you could also see that there's been a lot of developments in nuclear physics that use very powerful many-body methods combined with chiral effective field theory interactions, where we can now calculate nuclei up to 10, basically, based on these 2 and 3-body interactions. And then I discussed the nuclear physics features of response functions for elastic and inelastic WIMP scattering, both spin-dependent, spin-independent, and more general coherent responses like the WIMP-pion coupling. And the general message is that it's really important that you want to do as good as possible to just include the QCD and nuclear physics effects, so that you can really pinpoint to, if there's a signal, what is the BSM physics and what is the standard model physics. Okay, thank you very much, and I'd be happy to get more questions. Thanks a lot for listening.
Thank you, Achim. Are there more questions that you would like to ask?
Yeah, I have a question.
Go ahead.
Yeah, so I just wanted to see if you maybe have a backup slide to show your results for 7s.
No, I don't have a backup slide.
Could you just kind of expand a little bit more exactly what you did in that case?
Yes. Let me go to slide recommend. Okay, here, this is kind of an overview of, I think you may have to unmute, JJ. So here you can see all types of couplings between nucleons. So if the nucleon currents are vector, axial vector, or some other scalar and pseudoscalar. JJ, can you mute?
Yes.
Thank you. So then, much better now, I don't hear myself twice. So, but basically, and then coupling to WIMPs. So for the 7s response, we included basically the vector and axial vector contributions from the standard model. And we included the contributions from the nucleons. And you can see that at certain parts, there are also 2-body currents that come in. So we basically did vector and axial vector 1 and 2-body contributions, and we quantified, let's say, at which level axial vector contributions are important to this to the vector form factor. So at which is again not coherent, not contribution at a scale like the neutron number n squared, but scale like order 1. And we also provided response functions for other type of responses, because many of the 7th experiments have the goal to determine limits for BSM type interactions.
Right, I have a question, because a lot of the results that you showed, you were looking at WIMP masses, which are pretty heavy, right? And so in this case, you're also in that regime, or you're looking at other regimes in mass?
For the standard model contribution, of course, that we take the usual standard model particles. And I'm not sure I understand your question about the BSM physics. There we basically assume it's like a current interaction, and we
like what kind of graph would it be?
Yeah, let's see, where were they here? Like here. Okay, so there would be basically some mediator, and as long as you specify what type of current interaction it is, we calculate this side here, and then you connect it to whatever you want in your effective operators.
So I guess my question is, it doesn't really matter the mass?
Yes.
Okay.
Are you worried about, where was that? I'm worried about, in case these mediators would be very light, that you would resolve the whole thing?
Yeah, I'm just assuming at some point you can't go below a certain value on the mass threshold.
Mm-hmm. Yeah. So I guess as long as yeah, actually what we did in the paper, we started from this type of effective operators. So as long as that is valid, then you can use the formalism. Now, if you have other BSM models where this would be very light, then maybe that's not immediately applicable.
Okay, thanks.
So you didn't show anything about neutrinoless double beta decay. I mean, I guess these techniques are also being used there.
Mm-hmm.
I mean, do you know of progress in that area or?
Yes. So there are, let me go back. I didn't show this because I've not worked on it directly. I've worked on the current aspects of it. So let me go to maybe a slide earlier. So there have been calculations using these ab initio methods for double beta decay nuclei. The best studied case is not too experimentally relevant, which is calcium-48. But it's a great benchmark nucleus where different methods, similar to what I showed you for the oxygen chain, can be compared. And there are basically 3 of these methods here that have been used. One is the multi-reference in medium SRG, the valence space in medium SRG, and coupled cluster calculations. So basically these 3 methods have targeted calcium-48, and 2 of the methods have also looked at germanium-76 in particular. Now, all of these calculations, in fact, this is true for all calculations of double beta decay, use only the leading order currents. They just basically use this type of current twice, of course, and then you connect the neutrinos, effectively use this an operator based on these currents. The 2-body current contributions have not been considered in any calculations of double beta decay, because of neutrinoless double beta decay, because it is expected that they would generally reduce the matrix elements. Okay, so everything that I'm saying now is at the level of 1-body currents, and there these ab initio methods agree with each other among uncertainties, and for calcium-48 they find somewhat smaller matrix elements than the phenomenological calculations. And now one direction for future improvements is as you get heavier for the double beta decay calculations, there's also the issue that the interactions that are being used need to become more accurate. So in fact, a fraction of the community are working on designing better interactions for heavier nuclei. So this is the slide I showed you also for xenon based on the ab initio calculations. There's lots of scattering, and then also people want to use these two-body currents. And in fact, for the neutrino-less double beta decay in Chiral EFT, there's another short-range contribution just for neutrino-less, which is kind of an undetermined low energy constant that can be constrained in some few body sector, but it hasn't been included in many calculations. So Javier Menendez was somebody who looked into some estimates, and also Heiko Hergert, and from those we would believe that this two-body contributions may enhance the matrix element again. So I think at the moment the uncertainties in these calculations are still large for reasons of input and then two-body interactions, two-body currents not being included, and this one short-range coupling that enters from Chiral EFT in the neutrino-less sector having some uncertainties. And in the future, hopefully these three things will be improved. But the situation is much better than it used to be, in my opinion, compared to many of these old model calculations where there were basically parameters that needed to be adjusted to something in using that particular method. And I think the field is, in terms of Chiral EFT, gotten much more modern. Did that help you to put it in perspective?
Yeah,
or?
thanks. Thank you. Yeah, it's very interesting. Thank you.
Okay. Any more questions?
Okay. If there are no more questions, I'd like to thank Achim for this very intense talk, which clearly has resulted in quite a few questions, but I think we can actually follow up in lunch, because some of the more interested parties will join us now. So thank you again, Achim, and thank you everybody for attending the seminar. Bye-bye.
Bye.
Thanks a lot.
Bye.